Mr. Rajesh Gupta did his BTech in Electrical and Electronics Engineering from IIT Madras, where he won the Rama Sharma Kolluri Medalation for Best Academic Performance. He did MS in ECE from RPI, New York, USA, where he won the Henry J. Nolte Award for Best Academic Performance and Promising Future. His first full-time job at Rockwell Scientific Research, researching high-speed, high-power silicon and compound semiconductor devices, followed by Tram Incorporation. That was later acquired by Micron. In 2012, he moved back to India as the site leader and engineering head for Micron India R&D in Bangalore. In 2019, he joined AMS India as the country head and senior director of R&D engineering. He successfully led the development of several sensor products owned by the India design team, followed by successful commercialization for the business. Mr. Rajesh Gupta is a prolific inventor. He has more than 25 international patents to his credit. With this brief introduction, I request Mr. Rajesh Gupta to deliver a talk. Thank you.
I'll talk about one new trend that is happening for us in semiconductors and VLSI. That is that our systems are becoming more multidisciplinary, and that means like Professor Ram Gopal mentioned, his systems, they require multiple disciplines, and now you have to understand how do I optimize this new solution, which is not only a processor, which is not only a digital little piece of RTL or some analog electronics, but it has a lot of things. So we'll talk about that. So for example, right, in sensor-based systems, for instance, you could always see, for example, if there's an optical sensor in a phone, there's electrical signals for sure, there's lots of chips processing electrical signals. There's also mechanical design. How does light come in, go out? And what is the aperture size, what is the height, and so on, because in a smartphone this system, whatever you're designing, the sensor has to fit inside the phone or the watch or wearables, right? And then there is a thermal design, right, in the sense, what is the temperature of the sensors, because a lot of sensors are super temperature sensitive, so you have to be mindful of the temperature of the system. And finally, there is an optical design, so there are lenses, there are other ways that you focus light back so that you can make good sensors, right? So suddenly a problem of simply designing circuits now becomes really complicated, where you not only have to design the right circuits, but we have to optimize all of these, and each of these things affect one another, and I'll show you, right? And the same thing for, let's say, a different application, let's say battery management, right? So the same thing happens. There's electrical signals, there's mechanical design parameters, thermal design parameters, there's battery physics, and all of these things influence one another. You cannot design the chip without understanding all these interactions and keeping them into account. So, and the same, for example, for biosensors, that some examples were recently presented, right? We've also designed several sensors, for example, a temperature sensor with just 10 millidegrees of accuracy. Now 10 millidegrees is such a small temperature change that little things can change the temperature. Measuring it is a huge challenge. So all of these have to be solved. So for example, there are same electrical signals, mechanical, and then there's a bio contact which you need to optimize depending on what you're trying to measure. And then there's, of course, thermal and optical design. So as you can see in all these systems, it's not just about the electrical circuit design anymore. It has become more complicated. So how do we design these kind of systems, right? So first we'll look at how we do electrical systems. Electrical system itself is not a single system. Many systems, for example, you have digital processing, you have a memory subsystem, you have communication and networking, you have power management, you have signal processing. Now you may say, oh wait, this is all in a desktop. I can show you that all of these things are also on a little tiny sensor that goes into, let's say, your phone or something. So let's say we have a proximity sensor that we have designed for the phone, right? That can detect when, like Professor Raghav was saying, is, does the phone know if I'm there? Yes, it can, and it uses a proximity sensor to do that. Now this sensor is detecting light, right? So it has a small RTL circuit, which is a digital processing. It has OTP and P2 RAM and other memory systems inside. so that it can be programmed and it can be configured to do different things, right? It has a communication, so it has communication ports like SPI, I2C, other ports, so that it can communicate with the host. In this case, this little tiny sensor must talk to the host, which is a cell phone microprocessor, right, to communicate and do whatever the microprocessor is saying. It has, of course, power management circuits to deliver power to all the circuits that are on the chip, and then it's doing a lot of signal processing. So you can see that these systems are not just in big computers, but these are standard things in most, even small chips that we are making today. So even an electrical system is not only one system, but it has many, many systems inside. So what do we do when we are designing, right? How do we solve this problem classically in electrical design? Well, we do model-based behavior, right? So we develop models and we apply these models to run simulations and optimize them. So we build models. We have seen so many ways of modeling things. There are behavioral models you can make in Verilog or mixed signal. There's MATLAB models to model ADCs and other analog designs. There are SPICE models for transistors that you use for SPICE simulations, right, to verify the designs. There's models for layout parasitics. So we model everything. So in electrical IC design, what do? We model everything, then we simulate whatever we are trying to design and make sure it's working. Why do we need to do that? Because now the systems are so complex that we cannot just by hand and paper be confident that this is going to work. So that's the reason that to design these advanced systems and sense, you need models. So this is the way we've always been doing things. So in addition to developing models, now we not only do simple circuit simulations or only Verilog simulations, we do mixed mode simulations, we do simulations with more and more parameters and things joined together, right? And in this way, we design the parameters and the architecture is optimized and we get to a result. This is how we do standard VLSI design, right? Now, and what are the benefits of doing this, right? The main benefit is that we can optimize each component. We don't have to over-design for anything. We know what is a minimum that is needed and we can design for it. It can be a very efficient, energy efficient and area efficient solution and a very high performance solution, right? And most importantly, if you're able to simulate the entire system, if you can think of the whole system as your design and you can simulate it, then you have very high confidence that when the simulation or when the design comes into practice, it will actually work as you planned because there is less uncertainty. You have simulated all those things, right? And this is how we design these systems. So if you want to make state-of-the-art sensors, sensor products, or any new VLSI systems, right? It's not just enough to design only the VLSI or only to think of the circuits. You have to think of the whole system, like Professor mentioned. And here I'm going to show you 2 or 3 examples of how we did it, starting from a simplest approach, which is simply based on Excel, to something eventually much more integrated and complex, like using Python, and much interesting as well. So, of course, these are the 3 case studies I'll talk about. One is an optical optical sensor system to measure light and so on, and then there is a behind OLED proximity sensor system. This is kind of like the sensor exactly Professor Ramkumar was telling, where how does the phone know if a person is looking at it? It has a proximity sensor that is sitting behind the screen that's actually keeping track of what's in front of it. So we'll talk about how we did the modeling of that and made this sensor. And finally, we talk about a temperature sensor. This is the super accurate temperature sensor with very, very high accuracy for popular application like an Apple iWatch. You'll find this sensor over there, right? And so how do we qualify for such a tough supplier like Apple? You have to be the world's best, right? And we show you here some examples of what are techniques you can optimize your design and make them world class. So let's keep going. How do you make the system model and optimize, right? So the first example is the simplest of all. Hey, put everything up in an Excel, make all your formulas, put all the systems together, model everything and put it there. So I'll show you one example, right? Here is a simple example of a optical sensor, right, that I want to model. We maybe don't go into the specific details, but let us say these are some of my analog hyperparameters. There is some gain stages, some ADC, how many bits I want my ADC to be, what is my LSB, what noise I can have, what is my voltages, so on and so forth, right? And then I make a noise model. This we have developed from previous experience and understanding how that particular circuit works. That means What are my key parameters when I change certain sizes or capacitances or gains? How does my noise change, right? So I have already understood and modeled that and verified based on previous silicon, and so I have that model down in Excel now. So I have a noise model, I have these analog hyperparameters, then I have an optical model. This optical model tells me that when I have a certain amount of light shining, how much of this light comes back to my sensor that I can sense, how much is crosstalk, how much is other things. Maybe at this moment I do not have time to explain all of these components, but it's basically easy enough to understand that let's say there is an optical component, I made an optical model for it, I verified the optical model separately, and now have this model in Excel. I made a noise model for my analog, and I have my analog parameters. Now what I can do, I can put all of this together and make my complete system model. So now in this system model I can see, okay, what gain do I need, how much my light can vary. So here we needed to worry about the ambient light. So even though we are just sensing a reflected light, there can be stray ambient light in the room. The ambient light can be as high as sunlight directly shining on the phone, or room lighting, or it be very dark. So for all these cases, we wanted to make sure that when we go through all the calculations, do we have enough signal to noise, do we have enough range, are we saturating, is everything working right? So we are able to do all these calculations, and based on these we can optimize, because whenever things break, then we change those parameters, we change the gains, we change different things, right? Until we can solve this, and at least I call this on paper or on a sheet of Excel, we know that we have solved the problem. We know what gains we need to target, how we need to design, how we need to size our sensors, how should we design our optical system. So we have a great idea of how to do all this, and we know that if we achieve these parameters, we are very confident that our sensor will work really well because of this model, right? So this is one example of a very simple model tying together different complex systems, putting it together and running the model to have very high confidence that finally when I make this and realize this, it's actually going to work well. Well, you take this model and give it to a bunch of engineers, and what happens? It becomes hyper complex. Suddenly the engineers are so creative, right? They come up with so many parameters. So I made a very, very simple, call it one page or two page Excel model. Right? In principle, it's like the old Excel model, the first one I showed you, but it's much more detailed. Here, each individual model has been really filled with all the details and the formulas for it. So the noise and flicker model also became a lot more, call it more complicated and more precise, because there were different effects of different operating system, biases, so many more things that kind of got added on the noise model to modify it and make it more precise, right? So now we had this super precise noise and flicker model, and with this we were able to actually figure out a way to design our chip system to make this sensor to achieve what we wanted. Like, we had to limit the number of bursts to something small to meet the power budget, because this had to be in the phone and still achieve all our targets, SNR and everything. So I know at this moment it will be hard to explain all the numbers and how these came from, but the basic point is that you could still take that starting simple Excel model and really push its limit by having each individual model becoming much more sensitive and let's say with much more parameters, more accurate, but also more complicated. So this was my kind of second example of how you could take a simple, in this case it was an ASIC we were designing with a little laser and a photo detector sensor. So these three components make up our proximity sensor, which we completely design and let's say we sell. Next we say, okay, now we want to further push it. Now we already made the Excel model so complex, what more can I do, right? And next, one of the problems we had to do was to design a very tiny but very ultra precise temperature sensor. So we came up with the idea that instead of only using Excel, why don't we use a Python based system model. In this case, in Python, we will simulate the electrical behavior and the thermal behavior and all sorts of effects what we want to model, and then try to design the system. And I want to show you this. And what ended up happening, which was really cool, was that we could actually take this Python based system model and we were able to use it directly in design verification. You know, in design verification, you have to make a model of your electrical behavior, like a behavioral model. and you verify your actual simulation against what is expected from the behavior. So usually, these DV models are made by either mixed signal DV guys or design verification guys. They sit and write all these models in system Verilog, and it turns out that we could actually ultimately end up using this Python model itself, and I'll show you how we did it. It's really interesting. And so what we did was, first we made models for based on certain technologies and for different transistors. So in this case, it's a PNP. BJT was our sense element for the temperature sensing. So we actually made a BJT model. So what we did in the BJT model, you have corners. When you have a process, you have process corners, worst power, worst speed, and so on and so forth, right? And then there's a Monte Carlo corner. So you define these as a variable in Python, and based on this variable, you sort of start changing parameter values. And how you do this is actually you take the SPICE model, you open up that file, and you can almost automate it, or you can just look at it, you define the same names of the parameters, use the same formula, except now you can make the same SPICE model appear in Python, and now you can use it as part of your model. So we did this to a bipolar, we did this to a FET. Now I can model circuits within Python. Now I don't even need to go to a circuit model, right? It may not be 100% as precise, or we cannot make this super complicated like the SPICE model, but it could do very close to it. So we had the NMOS, we had the bipolar transistors, we wrote those equations for those, and we modeled them. So basically, just like how it is done in SPICE, we didn't do anything new. We opened up those SPICE files, and we just copied it and just turned them into Python. So it was pretty straightforward exercise. Now suddenly I have my bipolar, pipe, CMOS, and all these models available in Python. Okay, this is my first step. Next, I can easily start modeling IPs. Now that I have little building blocks like transistors, resistors, and these bipolars model, we modeled them as classes in Python, and then you can instantiate objects. So it's kind of same like Verilog, where you instantiate, an NPN, CMOS, and so on, and make your netlist. So in the same way, we just define classes for BJP, for BJT, I'm sorry, and MOS, NMOS, PMOS, so on and so forth, right? And then we instantiate it here. So you can see this is an object here, self.mp0. It's a CMOS of type CMOS. It's a PMOS with certain corner and with certain other parameters like length and width, because these are most common for transistors. So in this way, we define the circuit in Python. We construct it up, and then we use this method called __call_. What happens is whenever you call up this object, it will automatically evaluate this function. So through this function, you can re-evaluate whatever this IP needs to do. Since this was a bias IP, then whenever you call the bias block, it will run this calculation and tell you what is the amount of bias. So this is one example. But in this way, the important blocks can be modeled inside Python itself. So within Python, you modeled all the analog systems. So now let's say move on. Digital is very, very easy to model in Python, right? Python already, you could do lots of things with that. So very easily we were able to, in the same way, right, define a class for digital, right? And the same way kind of define our variables and define the digital RTL. This is, of course, a behavioral model, right? It's not how exactly the RTL is implemented, but it will do exactly what the RTL is doing step by step. So we can easily model what the RTL will do. So now we got the analog, we got the digital, we can add more components into the Python model, and now we have our entire system model ready, right? And how do we put together the whole system model? You can see here, so what we did, we have a thing called a class called top. So in this top, we have basically called the iBias, the ADC, the digital model, iDig, and the sensor model. So we put together all of these, connected them together, and again defined a call function like we did before. Call method calculates the results, right? So now we have a nice simple Python code that can, within a matter of less than a second or so, completely simulate my circuit. It's not 100% as precise. It's actually surprisingly close, but the thing is, you can do it very fast. What this means, you can try a lot of things. You can change a lot of parameters. You can optimize it like anything. You can add more components which are not related to electrical to this model, right? And you can optimize it. You can use all the functions available and libraries in Python to do automatic optimizations, like you could use some ML libraries, you could do other things. So it's all now there, and now at the start of the project, when we have such a model, I can easily now run through lots of parameters. I can do lots of design changes and quickly figure out what really works, what gives me the best result for my design set, including all the effects that I want to do. Right. And the advantage is this effect is not wasted. We ended up reusing these individual like iDig and the iSense and iBias back into our MSDV and DV simulations, where these same Python models can be imported, inside Verilog to run verification. And ultimately, yeah, we were able to optimize and make very, very precise. So this is the original temperature sensor. This is after some curvature compensation, and this is finally with all the corrections. So you can see we were able to achieve within 20 millidegrees of accuracy for this sensor. And this is not going to be so easy if you had to do mixed mode simulations and all of this, because it takes time and it's complicated. So this way you simplify your model, and at the model level you're able to model all the components and optimize them. And at the very start, near the architecture phase, you already know how you need to design, how you need to specify each of your individual circuit blocks, and that makes the design much simpler, and you're confident that near tape out, when you're doing the simulations for the full chip or as much as you can do, right, things are all going to work well because you already modeled most of it here and it's all working well, right? And the same thing happened. We were able to tape out in record time, and we have silicon that's working really well. So yeah, this was some effort that we did, and in using modeling in basically, since these days, like I mentioned, every electronic circuit has become like a system. There's a lot of interactions and a lot of hyperparameters. So this is one way that you can optimize and quickly get the results and be confident that your results are going to be, ultimately the system is going to work really well. Because the worst thing that can happen is, several months into the design, you realize, oh, I'm saturating, or I have too much gain or too much something else, and have to redesign everything from the back. Then you start all over again and do it, and it's a lot of time waste, right? So this is something that system modeling can avoid, and I've shown you now at least different ways: simple Excel, crazy complex Excel, and Python. So yeah, that's the summary. So modern systems, electronic systems are multidisciplinary and are complex, right? And VLSI design already uses model simulations to simulate and optimize, right? So this is just an extension. Why not extend it to also include the optical domain, the thermal domain, any other domains that are now interacting with our circuits, and model them all inside one system model. And yeah, and we showed you a couple of examples of this Excel-based model that really helped us, and then ultimately, also the more complex Python model that we were able to integrate using DPI. This is a programming interface that you can use to integrate Python models inside your Verilog simulations. So yeah, that's the thing. So what's next, right? Now that we have shown you how to do this, I think that this is really the beginning of this area, right? So this is still a lot more to be done, right? So of course we can use more and more of these for each design, but now you can start trying to use system model with a host software. Let us say in this case, right, our sensors were simple, they were hardware solutions. There was no software in our solution, right? But what if I had a software that was running on some hardware, and I had to also optimize my software, or I needed to try to define how do I hook up and do my software? Well, if you have a very good system model, you can also do that. You can use the system model within your software, try to give inputs to the model, get the outputs, and feed it back to the software, and run co-optimization using system model and software. So you could optimize those, right? You could integrate more and more diverse system models, more subsystem models, and include them to get better results, right? And every time you learn, you can further improve your model. You can take your model, calibrate it against whatever information you have, so you have high confidence that your model is working. So this is something we could do. And finally, right, we can also verify things like, sometimes we say, oh yeah, okay, I'm going to get a bunch of sensor data, and I'm just going to ultimately use it to develop some AI ML algorithms. It will self-learn and it will be able to do things. Well, how do you know it will work, right? Especially if you have ways that you can do these kind of simulations ahead of time, you have a higher chance of getting something done and getting a feasibility even ahead of doing this. So you could then apply these ML or AI algorithms to your system model optimization or system model software co-optimization, and optimize your whole system. So these are all, so let's say, future areas that we could still continue working on. So that's all that I had. Maybe I just take only one slide to talk about the company, what we are doing and so on. So we are, So that was the end of my talk, and we'll take questions with just one slide. That we have a program that we have launched with IIT Bhubaneswar to focus on VLSI training, and really this is a very rigorous program, and we believe this is needed. Like I think today, right, we need really smart VLSI engineers to write India's semiconductor future, right? And we believe this is a key area. So we've focused on this area now, and essentially the idea is to first have a launchpad that talks about the life cycle of an IC, right? How is an IC created? How the marketing and other teams come together to define the specifications of what a product makes sense, right? And then how those products are then designed, how the products then get into the market, how they ultimately become obsolete, right? We'll cover that. Then we cover industry landscape. What are all these different companies doing in the space of semiconductors? What is Intel up to? What is AMD doing? What is NVIDIA doing? What is Applied Materials up to? What is Synopsys doing? What actually are these guys doing in the business of semiconductors, right? Help students understand that, because we know and we are taught a lot about VLSI, how circuits work and so on. There is less universities covering courses about what the industry is doing. This is very important, right? Once you have this, you get a sense of the semiconductor business, how an IC life cycle goes through, what are all the specialties that go into making an IC through its life cycle, right? And then also the business of semiconductors. So then after the launchpad is an entrance exam that then students have to qualify. After that, they can go through the rest of the diploma program. This is a postgraduate diploma. And then they can do a foundation. So once again, a lot of places we found that there's a lot of focus on, let's say, digital design or analog design. But that's not enough. If you want to make a chip, verification is very important, right? Measurement is very important. Understanding semiconductor technology is very important, right? So we felt like the correct way to do a course is you need to cover all the basics. It's kind of like, if you want to learn cricket, first you learn all the areas, right? Get a basic sense of what everything is and know how to do that. And then ultimately, right, in the next semester, you kind of pick your choice. Hey, I'm really good at this. I'm really great with digital design, or I'm really great with analog design, or I'm very good with layout or verification, right? And then that's what you do your specialization on. And you do a project that would be at least industry grade. So this is a very rigorous course. And the idea is that you're already doing work equivalent to what you would do in your first job independently during the course itself. So that makes you really industry ready. And yeah, like all the talks before, this is a great time to be in the semiconductor space. So all the best to all of you who are working in this area, and you guys are the ones who are going to write our next future for the next couple of decades.
Thank you so much for your sharing your insights to us. I'm from Osmania University, and my question is, we can model BJT, FETs and also everything in Verilog or system Verilog. So what's the purpose of using Python as for modeling those things?
Sure, it's a great question, right? So we can already run SPICE models, right? Then why do we waste our time copying those SPICE models, adapting them to Python and making them work in Python, right? The point was not just to create sort of another system. The point then was that in Python, we can now add many more models, whatever we can think of, optical models, mechanical models. Maybe they're not available in Verilog, right? So all of these models, if we can already model something as complex as circuits, then all of these other things are much easier to include. So, and the reason to do it in Python is it's really flexible, and then we can keep extending it. So you're right. It was not to sort of replace, and we cannot replace the SPICE models because they are going to be much more accurate in Verilog. But the point was that if we have a simplified SPICE model, I can also now accurately model analog circuits in addition to digital. And now I can mix these with other models like optical, mechanical, thermal. I can add all of those together, and that was the point of doing it.
Okay, that is not possible by using Verilog or system Verilog.
Surely. So you can write models in Verilog and system Verilog. Now you start running Verilog simulations, right? Suddenly you'll realize that to simulate the chip, it takes you a day. Maybe to simulate the whole thing, it takes you a week, right? This simulation will run in 1 second. And right now you want to run many combinations. You want to go through hundreds of combinations, many bad designs, to quickly narrow down what design really works, right? You absolutely can do it in system, in Verilog and system Verilog. Everything can be modeled. It's just too slow. Why is it slow? Not because it's inefficient, it's very precise. The circuit simulation is super precise and it just takes forever to do all those simulations because these are not small circuits. There's lots of transistors. So once you're trying to simulate all these transistor behaviors and connecting those models together and everything, usually you have all of those also done by the time you're closer to tape out. And when you're very close to tape out, that means tape out is the point where you finish your design, right? You don't have time. There is pressure, like everybody is asking, are you going to meet your tape out date? Is everything working fine? It's like all this pressure, right? So you don't want to be optimizing at that point. You want to optimize very early in your project where maybe you have an idea of how the circuit is, but you haven't fully designed it yet. So that means you're not ready for the full Verilog simulations. If you can do something quick and simple. So that was the reason, like to move this, let's say system design to very start of the project at the architecture design phase so that we can get it all right and we can be confident that later it's going to work. So very, very good questions, but yes.
Thank you so much, sir.
In Python because it is far easy and efficient. After that, we need to do the back end of the PD, like the routing and
Sure.
all right. No, so that again we'll come back to the tools which we use standard, or else we can do them in Python.
Sure, no, that's a good question. Once again, right, this Python model is not going to replace the verification that we do in SPICE and the full system checks, right? We still have to do those. The reason to do this simpler version in Python ahead of time is we can do the optimization and optimize the system before we start to even design the electrical circuits. So yes, it's not going to be precise, it's going to be close, right? So there can be rooms for error, but the hyperparameters, that means some things that are hard to imagine, like, okay, what range of gain I should keep, how many bits should my ADC be, right? I cannot decide how many bits my ADC should be sort of after designing. I have to know that first, then I can design. But these are things I can now vary in my model and optimize all these things and know that my system works and then start the design. They will not replace the verification. You still have to do all the verification like we do in VLSI because that's much more precise. This is just for the system optimization.
Thank you, sir.